Okay, this is a case study where we will be trying to optimize the design of a reverse Brayton Cryocooler. So this is the schematic of the cryocooler. You can see it's a simple recuperated reverse Brayton Cryocooler. There's a compressor and a turbine that are connected to the same shaft. The stuff that leaves the compressor goes to the aftercooler, where it rejects heat to the surroundings, or if it's in space, maybe a radiator. Then it goes through the hot side of this recuperative heat exchanger, where it's cooled to a low temperature, and it goes through the turbine down here, and it's expanded to cause the temperature drop. And this very cold, low pressure fluid goes through the load heat exchanger. That's where the refrigeration is being provided at, in this case, 80 Kelvin. And then the stuff leaving the load heat exchanger goes back through the other side of the recuperative heat exchanger, the low pressure, the cold side, and returns to the compressor. So we've numbered the states here, 1, 2, 3, 4, 5, and 6. And there are some parameters that are given to us. So the heat exchangers are specified either in terms of their approach temperature difference for the aftercooler or the load heat exchanger, or the recuperative heat exchanger, the conductance has been specified. And for each of the heat exchangers, you can see there's a fractional loss of pressure assigned to it that we need to take into account. What else? We have specified that the pressure ratio across the compressor is 1.8. We're going to assume that the working fluid is neon at these temperatures. And then we've also specified that the lowest pressure in the cycle, which is the suction side pressure on the compressor, is 200 kilopascals, and that the shaft speed is 2,500 revolutions per second. And with those parameters, we need to design the compressor and the turbine so that they have the best possible efficiency. So that's going to be a design exercise where we'll need to use some kind of curves. Maybe in the component library we'll find the Balje curves programmed, where we can try to optimize the efficiency of a compressor, a radial compressor, and a radial turbine for these conditions. And it says also, once we have the simulation working, we ought to explore how those conditions, so the pressure level and the speed, affect the performance of the cycle, and also the size of the turbomachinery, because making very, very small turbomachinery that spins very fast is more difficult than making bigger turbomachinery at this scale. Also, the mass flow rate is 16 grams per second. So that's the problem that we have. This is a design point problem, not an off design problem. We're trying to design the turbomachinery for one condition. So I'm going to classify the inputs as operating conditions, and these include the lower pressure there and the pressure ratio, those two temperatures, the heat rejection temperature and the load temperature, the shaft speed and the compressor inlet pressure, at least initially, are just given operating conditions. Eventually we'll vary them. And then we have a bunch of performance parameters, which are these approach temperature differences for the aftercooler and the load heat exchanger, all of these pressure losses, and the conductance in the recuperator. And then I'm going to try to map out a strategy for solving this. So actually, okay, let's think about this. The first thing I know is all the pressures in the cycle, I think, right? I know the pressure entering the compressor is 200 kilopascals. The pressure leaving the compressor is 1.8 times that. And then as I go through each of these components, I'm going to lose some fraction of that pressure. So I'll lose a little pressure in the aftercooler, but that's specified by this. So I know P3, lose some more pressure on the hot side of the recuperative heat exchanger, so I know P4. And then if I go the other direction from state 1, I must gain a little bit of pressure going from 6 to 1, so I know P6. And then I gain a little more pressure going from 6 to 5, so I know P5. So I know all 6 pressures in the system. So that's one intensive property at every state. So what else would I do then? I know that the temperature leaving the aftercooler must be the heat rejection temperature plus the aftercooler approach temperature difference. So that completely specifies state 3. I think I can do the same thing down here on the load heat exchanger. The temperature leaving the load heat exchanger must be the load temperature plus the load heat exchanger, I'm sorry, minus the load heat exchanger approach temperature difference. So I know T6, that specifies that state. If I know 3 and 6, then if I go to the component library and pull out the right model of a recuperative heat exchanger, it ought to tell me how that's performing, allowing me to get the enthalpies leaving at state 1 and state 4. So that would fix states 1 and 4. So that only leaves 2 and 5. Which I would know, which I would be able to get if I knew the efficiencies of the compressor and the turbine. But the whole point here is that I am going to design the compressor and the turbine, so I got to come up with the design that maximizes their efficiency. And so what I'm going to do then to get from 1 to 2 or from 4 to 5 is I will use those Balje curves. So I'll figure out, for example, at state 1, what's the specific speed under these conditions, and based on the specific speed, I can go to the Balje curve and figure out, okay, what's the optimal specific diameter, and therefore what's the diameter, and what's the efficiency at that condition, which would then let me figure out state 2. And the same thing for the turbine. So that's my strategy. There's no real iteration that has to happen there. It's all very sequential. And when I get all done with the model, then I can come back and maybe visualize what the parameter space looks like in terms of P min and N, and try to understand what is the best combination of pressure and speed that gives me a cycle that both performs well and also has turbo machinery that's as big as possible. Okay, so this is the beginning of the ease code that we'll use to solve this problem. Just a few things that I've already done here so you don't have to watch me type is the first thing I did is load the component library, because I know I'm going to be using that for the recuperator as well as for the turbine and the compressor. I set the unit system, of course, because I'm going to be using thermodynamic property functions. And then I put in the operating conditions, so that's this stuff here. This is the fluid we're going to use as neon, the two temperatures that we're operating between, the pressure ratio and the mass flow rate. And then I have set initially the optimization parameters. So these are the parameters we're going to eventually vary to maximize the performance. So that's the minimum pressure, so that's the, I guess, the compressor suction pressure, and then the speed of the shaft. And then the next set of values here are the performance parameters. So these are the heat exchanger performance. This is the approach temperatures of the two heat exchangers that represent the aftercooler and the load heat exchanger, and then the conductance of the recuperator, and then the fractional pressure drop for every single heat exchanger. Okay, and then finally I went ahead and set all of the pressures in the cycle. Again, the suction pressure is P min. The discharge pressure is the suction pressure times the pressure ratio, and then as I move downstream I just lose a little bit of pressure as I go through the aftercooler and then the hot side of the recuperator, and then on the other side I'm going to lose some pressure as I go through the load and then through the cold side of the recuperator. So I have all the pressures set, and now I'm going to sort of employ that strategy that we talked about as we looked at the schematic. So the first thing I'm going to do is recognize that I know T3 because I know the approach temperature difference of the load of the aftercooler. Sorry, so this is going to be the heat rejection temperature plus that approach temperature difference. So I know T3 and P3. That means I know every other property at state 3. So I'm going to go ahead and get the enthalpy using neon at T equals T3 and P equals P3. And I can copy this and just change this to entropy, and maybe I want specific volume. I'm not sure why I would, but let's go ahead and get that as well. So this is entropy and this is specific volume. Entropy, volume. And before I move forward, I probably ought to go ahead and solve this. Make sure I haven't made any mistakes. I'll go look at the arrays table. Yeah, it looks like so far so good. Okay, so that's one state that I know. The other state I know is the state coming out of the load heat exchanger. So T6 is equal to T load minus DT load. So I know the temperature and pressure coming out of the load heat exchanger, so I can go ahead and get everything else. So H6 equals enthalpy of F dollar at T equals T6, P equals P6. And I'm going to go ahead and get the entropy and the volume just like I did at state 3. So this is entropy and this is volume. And we will calculate it. Looks like it solves. Everything looks good here. Okay, so that's states 3 and 6. Those are the inlet states to my recuperator. So I'm going to simulate the recuperator knowing the conductance, the pressure drops, the fractional pressure drops in those inlet states. So I'll go to function information. I'll select the component library. It's already been loaded. I loaded it with that directive, so I have to go to heat exchangers. And then I have to find the one that I want. So this one looks okay, but I think if I look in the help, this is going to assume constant specific heat capacities, which isn't exactly what I want, given that neon's behaving less a real fluid. So probably this is the one that I want, right? This is a counterflow recuperator using the sub heat exchanger model, which means it's actually going to account for the heat capacity variation with the given UA. So I'm going to go ahead and paste that in here and manipulate the inputs and the outputs so that they match my situation here. So both sides, the hot and the cold side, are neon, so those are both F dollar. This CH is concentration, which would be only something I would need if I were using a brine. So these concentrations I can set to basically anything, but I'll set them to 0%. And then I have pH in. So let's see, this must be coming out of the aftercooler, so I think this is P3, and HH in, this is H3, and this is M dot, and then PC in is coming out of the load, so this must be P, what is it, 6 I think, and this is H6, and this is also M dot. Both sides have the same flow rate. This is the UA of the recuperator, which I call UA recuperator. This is dP over P of the recuperator on the hot side, and this is dP over P of the recuperator on the cold side, and this N is the number of sub heat exchangers to use. So I could play with this. I'm just going to use 10 to begin with, and what this will predict for me is HH out, which I think is H4. This is what's going into the turbine, and HC out, so this is H1, that's going into the compressor. If I want to know the recuperator effectiveness, I can get that. And if I want to know the approach temperature difference, I can get that as well. So hopefully that will solve. Let's save this and solve. And it looks like, yeah, it looks like it does okay. Let me head over. Under these conditions, the effectiveness of the recuperator is 0.994, which seems really high, but for these cryogenic recuperative heat exchangers, that's not unheard of. Alright, so I have now the, what do I have? I have the enthalpy and pressure at state 4, so I can get all the other properties at state 4. And I have the enthalpy and pressure at state 1, so I can get all the other properties at state 1. So I might as well go ahead and do that. T1 is equal to the temperature of F dollar at H equals H1, and P equals P1. And I might want the entropy and the specific volume. So S and V, this is entropy, and this is volume. Now we'll do the same thing at state 4. So I know the enthalpy and pressure at state 4. So T4 is equal to the temperature, F dollar, H equals H4, P equals P4. And then I have S4. Let's just copy this twice. So this is S4 and V4, entropy, volume, and make sure that also runs, and it seems to be okay. So I've gotten 4 of my 6 states now. I'm missing the state coming out of the compressor and the state coming out of the turbine, and to tackle those states, I'm going to have to go use the Balje curves to try to predict what is the efficiency that I might be able to achieve using a radial compressor and a radial turbine under these conditions, and that's the next step. All right, so at this point I have to deal with the compressor and the turbine. So let's start with the compressor. And in order to use the Balje curves, maybe I first want to look at how they're put together. So let's go to options, function information. Let's see, I'm going to start with the compressor. So that's up here. There's a bunch of different compressor models. I'm interested in these two, right? So these two models, the first one tells me if I give it a certain specific diameter and specific speed, so these are dimensionless parameters, it will tell me what the efficiency would be for an on-design compressor based on the Balje curves. And if you look at this map, you can see that there's sort of an optimal value. So there's if you give me a specific speed, there's clearly a specific diameter that maximizes efficiency. So that's what the second one does. It says if I give you a specific speed, so some specific speed along here, which I can calculate knowing the speed of the shaft, then what is the specific diameter that I would want to choose in order to get the optimal efficiency. So I'm going to need to use both of them. Now I'll start with this one, and then I'll move on to this one once I have the NSDS combination. So let's look at the function information to see how specific speed and specific diameter are defined. So you can see they're defined using these equations here. Like I said, they're dimensionless. I'll copy these and get rid of this. So first thing I'm going to want to do is calculate specific speed. So this is the specific speed of the compressor, and the specific speed of the compressor is the speed of the compressor times the square root of the inlet volumetric flow rate divided by the isentropic enthalpy rise of the compressor. So I'm going to need to calculate those three parameters. Let's do those one at a time. Omega is equal to, I didn't calculate that already, did I? No. Omega is equal to the speed in radians per second, right? So let's see, the speed in radians per second would be n times convert from revolutions per second to radians per second. All right, V dot is the volumetric flow rate. I should call this V dot C probably. The volumetric flow rate at the inlet to the compressor. So the inlet to the compressor is state 1. So I'm going to take the specific volume of state 1 and multiply it by m dot. And then finally, dH sub S is the isentropic, we'll call it dH sub C, the isentropic enthalpy rise across the compressor. So that's going to be the enthalpy at P equals P2 and S equals S1. So that's the isentropic enthalpy at the exit of the compressor minus H1. So the NSC then is omega, which I've calculated, V dot C, and then DHSC. And this should solve and give me a specific speed of 0.309 radians. So now that I know the specific speed, I can use this to get the optimal specific diameter that would maximize the efficiency. And again, I'm going to go to function information. I'm going to choose not this first one, but the second one. So I give it the specific speed. It gives me the specific diameter. We'll paste that in there. So the specific diameter is that specific diameter based on the specific speed. And that's going to be a dimensionless number. So I'm not sure where it is. It's right here. It shouldn't have any dimensions, and it doesn't. And then finally, let's do this. I have to turn this specific diameter into an actual diameter. So I'm going to use this equation for that purpose. So this is specific diameter. Let's see. The diameter of the compressor, the isentropic enthalpy rise, and the volumetric flow rate. And that should calculate the actual diameter. So the actual diameter of the compressor is right here. It's 1.87 inches. And then finally, I can take the specific speed and specific diameter, both of which I know, to get the efficiency. So I'll go back to function information. Now I don't want to use this one. I want to use compressor 5, where I give it NS and DS. And then this is an eta max that I can give it if I don't want to use the eta max that the Balje curves would predict. So if I want to scale up or down, I think I'm going to not give it eta max. Instead, I think if you give it a negative number, it'll ignore this and just give you the eta predicted by the Balje curve. So eta C, that, and that. And so the Balje curves would predict under these conditions that the efficiency of the compressor is 70%. Right? And then finally, I can use the efficiency of the compressor to get state 2. Right? So H2 is equal to H1 plus DHSC, and I have to divide that by eta C. So I know H2 and P2, I can get everything else about state 2. T2 is equal to the temperature of neon at H equals H2 and P equals, P2. And maybe as long as I'm getting properties, I should get S and V. So this is S, this is V, this is entropy, entropy, and this is volume. And we should solve and make sure that it solves, and it's going to give me, yeah, now I am 5/6 of the way done, at least in terms of my states. Alright, so let's do the turbine. The turbine is basically exactly the same process, but using the Balje curves for the turbine. So I already know omega, it's spinning at the same speed. Let's do V dot turbine. So this is again the inlet volumetric flow rate, so that's going to be, I think, V4, so M dot times V4. And I also need the isentropic enthalpy drop across the turbine, so DHST is equal to H4 minus the enthalpy at P equals P, I think it's B5, right? P equals P5, S equals S4. So now I can get NST, so that's what I'll do here. Same definition for specific speed. T, omega is the same. I got to use V dot T and DHST. And now I can use the equivalent Balje curve model. So let's go here. We're not talking about compressors anymore. We're talking about turbines. So we'll go to turbines. Again, I want to use this one to tell me what the specific diameter should be at that specific speed. So I'll paste that in. This is DST. This is NST. I'll turn that specific diameter into an actual diameter. So that's what this equation will do. T, that's a T, that's a T, and that's a T. Maybe we should solve and make sure I haven't made a mistake. So the turbine diameter wants to be, where is it here? 0.5535 inches. Okay, and then we'll go ahead and get the efficiency under those conditions. So again, go back here and use the other function. So this is the one where I give it NS and DS, and if I want eta, so this is eta T, this is NST, DST, and again I'm going to not scale the Balje curves. I'll just put a negative number there. And then finally, now that I know the efficiency, I can figure out state. I guess it would be 5, right? So H5 is equal to H4 minus eta T times DHST. I know H and P, I can get everything else. So T5 equal to the temperature of neon at H equals H5 and P equals P5. Now let's go ahead and get entropy and volume, specific volume. So this is S and this is V. This is entropy. And if I could spell entropy, wow, and volume. Alright, and if I solve, I find that now I have all of my states and they all look okay. There's no unit problems. Let's just finish up the model. If I want Q dot load, that's an energy balance on the heat exchanger, the load heat exchanger, so that would be M dot times H6 minus H5. If I want W dot C, That's an energy balance on the heat exchanger, so that's H, I think it's 2 minus H1. If I want Q dot heat rejection, that's an energy balance on the aftercooler, so that's H 2 minus H3. And then finally, the turbine power is W dot times H 4 minus H5. H5. So the performance you can get in different ways. I'm just going to calculate the COP. The COP here is going to be the cooling that I get, Q dot load, divided by the net power in, so W dot C minus W dot T. And the COP of this is 0.1156, which seems really low, but this is a pretty low temperature, so the best COP you can get is only going to be a little bit better than that. Alright, so that's the model, and then the next thing I'd like to do is manipulate the model to do some optimization, and specifically the optimization would be, let's maximize the COP by varying these parameters, and keeping in mind that I would like my turbo machines to be as big as possible, because those are the kinds of turbo machines that are easier to make. Alright, so because this is a two-dimensional optimization, we have two parameters. Rather than use the optimization algorithms and ease, I'm just going to build a contour plot that shows both the COP as a function of these two parameters, and then on top of that I'm going to put lines of constant compressor or turbine diameter, so that we can see how both those things affect it. Sometimes that's a nicer way of doing it when it's just two-dimensional. So let's see, the first thing I got to do is have a new parametric table. In the table I'm going to put, let's see, 400 rows, so it'll be 20 by 20. I'll put COP. I'll put, what else I got to put in here? The turbine diameter and the compressor diameter, so these two. And then I also have to put the speed, I guess, and the compressor suction pressure. I could put other things as well, but I think that's probably good enough. So I'm going to vary the speed from, let's say, 1,000 to 10,000. So here I'll do alter values from 1,000 to 10,000 revolutions per second. I'm going to go ahead and repeat that pattern every 20 rows. So that should just repeat this over and over again. And then I'm going to vary the minimum pressure from, let's say, 50,000 to 500,000. So 50 kilopascals to 500 kilopascals. And I'm going to apply that pattern every 20 rows. So this gives me a complete grid over that range of speed and pressure. And then I'll go ahead and solve the table. So before I do that, I'll want to comment these out. And we'll come back to here. Calculate solve table, and we'll solve it in reverse order just to be sure it solves. So you can see it working backwards through these runs. Okay, so now I'm going to want to make a contour plot showing COP in this parameter space of N and P min, and then either DT or DC. So let's do that. I'll start with COP, so XYZ plot. This is table 3, I guess. So the x-axis might be N, the y-axis could be P min, and then the contour variable is COP. And I'm going to make color bands, and you can play with the resolution and you can play with the interpolation scheme, but hopefully this will work okay. And there's the outcome. So you can see there's a range of P min and N that sort of puts you on top of this plateau. So you'd want to be up here in order to maximize COP. Right, that's going to get you your maximum COP here. And then the question is sort of where do you want to be? And that's going to be related to other considerations, and one of the key considerations is I'd like my turbo machinery to be big so it's easier to make. So to do that, I can overlay onto this plot. Let's see, let's do this again. Overlay. I didn't want to do that. So do plots, overlay plot, overlay contour, and again, X is N, Y is P, but now maybe the contour variable is DC, and this is going to only put lines on here. And yeah, those are my plots. These are my lines of constant diameter. So I don't know, it looks to me like if I want to make my turbomachinery as large as possible, I'm going to be wanting to be down here where the compressor gets to be maybe 1.3 or 1.4 inches versus up here where it's maybe only 3/4 of an inch. So bigger compressor that's running more slowly is going to be a little easier to make, and I can do that if I go to lower pressure and lower speed.